My talk today is based on this preprint here. Can you see my mouse? Or okay. It's a joint work with Christopher Janjigyan and Timo Seppalainen. So although I'm currently based at KTH, this was a project that began a couple of years ago when I was a postdoc at Carnegie Mellon University. So let me begin with an outline. I plan to divide this talk into 4 parts. So first, I will describe the increment-stationary exponential last passage percolation. This will be our main setting. Then I'll present our main results on the right tail of the so-called exit points in this model. So our results provide optimal upper bounds, optimal tail upper bounds. These are optimal in order. And it turns out that exit point bounds find some applications in study of some geodesic related objects in LPP, including the competition interface and Busemann limits. So in the third part, I will mention some applications related to these. So these are useful objects for describing the geodesic structure in the LPP. Then in the final part, I intend to talk a little bit about the technical aspects. So specifically, I will comment on the starting point of our proof. Okay, so let me begin with describing our setting. So let's consider the positive quadrant of the integer lattice. So to each vertex, we assign an independent exponential 1 distributed random weight. Now I will be working with upright paths between vertices. So this is an example of an upright path. At each step, the path goes right or up 1 unit. Then the main object of interest in this model is the so-called last passage times. So between vertices x and y, these are defined by this formula. So for each path from x to y, we sum up the weights along that path and take the maximum. And this big pi xy denotes the set of all upright paths from x to y. Okay. Maybe it's not necessary for this audience, but just in case one is wondering why we are doing this construction with the exponential weights instead of just any other weight distribution, this exponential LPP holds a special place for a few reasons. The first, it arises naturally from other important models, such as the totally asymmetric simple exclusion process, or from the queuing literature. And it's also an integrable member of the KPZ universality class. This is well known since the seminal work of Kurt Johansen in early 2000s. So for us, this will be a prototypical setting to develop our arguments, but as I will argue later, the arguments we develop has potential to extend beyond this model. Okay, so what I will actually consider is not the is a variation of the exponential LPP that has additional boundary weights. So now let's again start with exponential 1 distributed random weights, but now I also place these weights on the axes of the first quadrant. Okay. Now what I will do next is to rescale the parameters of the exponentials on the axes. So for each weight on the horizontal axis, I multiply by 1 over w, so w is a positive number. So this makes the horizontal boundary weights exponential w distributed. And for each vertical boundary weight, I multiply by 1 over 1 minus z, where z is less than 1. So this makes the vertical boundary weights exponential 1 minus z distributed. And then the weight at the origin is irrelevant, and it's just set to 0. And the last passage times in this model is defined just by the same recipe, except that we are now using these modified weights, which I will denote by omega wz. Now, models of this type go back to at least the work of Jinho Baek and Eric Rains, who studied Poisson last passage percolation, also known as Hammersley's model with boundary weights. There's also an earlier work, related work preceding this by Prahofer and Spohn on polynuclear growth model. The process I will be most interested in is this special case of last passage times. So I will now choose W parameter equal to Z parameter. So the horizontal weights are exponential Z, and the vertical weights are exponential 1 minus Z. Then it's known that, so if you look at the last passage times from the origin to other vertices, now this forms a process. Now this process has stationary increments. So what do I mean by this? So more precisely, so if you look at the last passage times from the origin to x plus y, and from the origin to x, then the difference of these has the same distribution as the last passage times from the origin to y. So one consequence of this increment stationarity is that, so if you look at the increments of this LZ process along any horizontal level, then these increments will just have the same distribution as the horizontal boundary weights. So this distribution exponential z just gets translated across the horizontal lines. Likewise, if you look at the increments of the LZ process along any vertical line, those will also have the same distribution as the vertical boundary weights. There's actually a stronger distributional property that this model satisfies. This is so-called Burke property. Now, I will just state a part of this property that will be relevant to this talk, which is the following. So if you take any downright path, as shown in the picture, and look at the increments of the LZ process along this downright path, then the increments along this downright paths are also independent. Now, in this talk, our main results will be derived entirely from the increment stationarity property. And the two applications I mentioned related to geodesics, they use the stronger downright property. Now we specifically limit our tools here to this increment stationarity and exclude tools from integrable probability and random matrix theory. For example, we do not use the connections to Laguerre unitary ensemble or Fredholm determinant representations of the distribution of the last passage times. Now, what's the motivation behind this constraint? So there are a few reasons. So first one is that this increment-stationary structure is known explicitly for the integrable examples of directed last passage percolation and directed polymers. So this slide includes possibly a non-exhaustive list of such models. And the references are possibly also incomplete. So I intended to include where the models were first appeared and also where this increment stationary structure were first utilized. So the case we are discussing here is this exponential model with weak paths, but the structure of our arguments has the potential to be generalized to these other settings as well. Now, another reason is that, for example, although integrable probability and random matrix theory provides powerful tools, some of these tools are either not available or not entirely developed in all of these settings. So for example, the exponential model relates to the eigenvalue process of the Laguerre unitary ensemble, but such a connection is not present for the case of Bernoulli models, for instance. Also, in all of these cases, the distribution of the last passage times can be expressed in terms of some exact formulas coming from integrable probability, but these can be somewhat challenging to work with, especially in the case of positive temperature. So in any case, so our purpose here is to develop some alternative methods that that could be applied in all of these settings that can be adapted as needed to these settings without too much technical difficulty.
Sorry, so like what's the difference between this weak path and the strict path? Like what does that mean?
Yes, thank you. So weak here means that each coordinate of the upright path it forms a non-decreasing sequence. So at each step, it can go up or right, so it can stay the same. So one coordinate can stay the same. But if you have a strict path, it means both coordinates must increase at each step.
I see. Thanks.
Okay. And one other reason for our development is that stationary, also known as the equilibrium versions of the directed percolation that we use. So these versions exist under fairly weak conditions on the weight distributions, both in the case of polymers and in LPP. For example, it suffices to have 2+ epsilon moments for the weights. So this is quite speculative now, but the arguments based on stationarity can potentially be generalized beyond the integrable models. Now, of course, this would, if this is feasible, it would require substantial work, but it's not entirely a far-fetched idea, because at least for some problems, this program has been successful. So for example, for general i.i.d. weights, it has been possible to describe limiting shapes and some limiting properties of geodesics through stationarity. Okay, so after this conclusion of the part 1, now I will move towards stating our main results. Okay, so I will need a bit of notation. So let's recall this process LWZ. It's the last passage times that use boundary weights. So this was the formula. Now, almost surely, there's a unique path that maximizes this quantity. That's called the geodesic from vertex x to vertex y. So here, the green path represents the geodesic from the origin to vertex x. Now consider this geodesic. Then I will define the exit points of this geodesic from the axes. So the horizontal exit point is defined as the largest, the number of vertices that it visits on the horizontal axis before entering the bulk. Similarly, the vertical exit point is the number of vertices it visits on the vertical axis before entering the bulk. So for any realization of the weights, exactly one of these quantities is zero. But which one depends on the realization of the weights. Now, our focus again will be on the increment-stationary case here. So I'll take W equals Z, so the horizontal boundary weights are exponential Z, and the vertical boundary weights are exponential 1 minus Z. Now, when Z is small, meaning close to zero, then the horizontal boundary weights, they have larger means. So the geodesic from the origin would prefer going right initially. Likewise, if Z is large, so meaning Z is close to 1, the geodesic from the origin would prefer going up initially. So it turns out that one can actually describe the transition point precisely for this model. So it's given by this function zeta here. If Z is less than zeta, it turns out, the geodesic prefers going right. If Z is bigger than zeta, much bigger than zeta, then it prefers going up. So when Z is in the vicinity of zeta, then both of the exit points are small relative to the sizes of the rectangle. So these conditions, so this first condition can be also equivalently expressed in terms of the direction of the northeast corner Mn. So it's just saying that that corner is approximately has the direction of this characteristic direction defined by this vector here. Now, our main results in this talk are concerned with some fluctuation bounds for the exit points. So I'll look at two regimes separately. So the first result concerns the regime when we are around the characteristic direction. In that case, both of these are small. So the statement is that we fix a distance delta, small parameter delta, and a non-negative number k. So in the statement, this S delta here denotes the set of lines with slopes between delta and 1 over delta. So we want to restrict attention to points away from the boundaries in order to have uniformity. Then there are some constants, C0, N0, and S0 with these indicated dependencies, such that either of the probability of either the exit point being bigger than S times M plus N to the 2/3 goes down like e to the minus C0 times S cube. So this holds provided that S is large enough, Mn are large enough, and Z is within M plus N to the minus 1/3 of the critical parameter zeta. Now here, let me remark about this condition on Z. Again, so it just means that the northeast corner of the rectangle has approximately the characteristic direction within an error of m plus n to the 2/3. Okay, now soon after we posted our preprint, there was an independent work by Manan Bhatia, who also essentially obtained this result, but using other methods, namely utilizing sharp tail bounds for the Laguerre unitary ensemble, coming from earlier work by Ledoux and Ryder. There's also a preceding work by Promit Gosal, Patrick Ferrari, and Peter Nayar, who obtained a Gaussian upper bound for the exit points in a similar setting. So they considered half space LPP bounded by some anti-diagonal, and in that setting one can also define a notion of exit point, and then they obtained this type of a bound. Presumably their arguments would also can also be adapted to here in our setting.
Can I ask you a question?
Sure, absolutely.
Can you give some intuition why do we have like s cube kind of bound here? Because usually it is like s to the power 3/2 for upper tail.
Okay, so that's a very good question. But I guess
is this really actually like related to the lower tail of trace rhythm instead of the upper tail?
Well, lower tail of the LPP does come in the proof.
Okay.
Although so the lower tail of LPP goes down like s cube, as in this bound, but actually to obtain the s cube bound here, one just needs to use s to the 3/2 left tail bound for LPP. So the s cube does not immediately come from the cubic tail decay on the left tail for LPP. I guess, right, so I don't immediately have a simple answer to your question, I'm afraid. Maybe towards the end of the talk, I may try to attempt to answer again, but right away I don't have an answer, sorry.
Thank you.
So, right, okay. Yes, so I was saying that, right, so Patrick Ferrari and co-authors, they also obtained a Gaussian bound in which they used this left tail bound s to the 3/2 for the last passage times. This comes from an earlier work by Bake, Ferrari, and Péchet, and they in turn use the connection to Laguerre unitary ensemble and some saddle point analysis utilizing an idea from Harold Witham. So this is the type of argument that we are trying to avoid here. Our proof relies only on the increment-stationary structure. So now the question might arise if whether we are proving the left tail bound for LPP needed to derive this result using stationarity. The answer is no. Actually, we don't rederive it. We just somehow circumvent this left tail bound. So these bounds, these type of left tail bounds, still remain inaccessible via the increment-stationary LPP. So restricting to increment stationarity, the best previous bound that was available in the literature was of polynomial order, 1 over s cube. So we improve this to the optimal bound. Now, why do we know this is the optimal bound? Because a matching lower bound has also been recently obtained by Timo Seppäläinen and Xiao Shen, adapting a change of measure argument from an earlier work by Marton Balas and Seppäläinen. So S cube is the true rate of decay for this. Okay. Now I will look at the second regime. So we looked at what happens around the characteristic direction. Now we consider the situation away from the characteristic direction. Now I'll again fix a delta as before. So I will restrict attention to this cone away from the boundaries. Then there is a constant C delta such that the following bounds hold. So if Z is smaller than critical parameter, as I mentioned earlier, the geodesic prefers going right. So the vertical exit point here should be 0 in most cases. So we are bounding the probability of an unlikely event. And this probability, again, goes down like m plus n times the difference of the critical parameter and Z cubed. So there's also a cubic decay here. And similarly for the horizontal exit point when Z is above the critical parameter. Now, so you see the condition that Z is within m plus n to the minus 1/3 of the critical parameter was that the vertex Mn being m plus n to the 2/3 of the characteristic direction. So for this bound to be decaying exponentially, one needs to be away more than m plus n to the 2/3 from the characteristic direction. So this is really useful when one is away from the characteristic direction. Okay, so previously a Gaussian upper bound for these probabilities were obtained by Patrick Ferrari and Alessandro Ocelli. Their bound was Gaussian. And again, their argument relied on this s to the 3/2 left tail bound for LPP. Okay, so this concludes the main results that I wanted to include in this talk. And in the subsequent part, I will just mention a few applications of these. So these applications will concern the bulk LPP. So one can couple the bulk LPP with the increment-stationary LPP. And in this coupling, it's important to control where the exit point is. And then with good control, one can get good bounds on various quantities in the bulk model. So in the bulk model, again, recall that the weights are exponential 1 distributed and independent. And between any two vertices, ordered vertices, there is a unique, almost surely unique upright path. So this green path represents the geodesic from 1, 1 to vertex x. Now what I will do is I'll consider a larger grid and draw the geodesics from 1, 1 to every other vertex on this grid. Then due to almost sure uniqueness, almost surely I will get geodesic tree. Now I will divide this geodesic tree into two parts. So into a red tree and a blue tree, depending on how they are connected to the root here. So the red tree is connected through a horizontal edge, while the blue tree is connected via a vertical edge. Now we can separate these two trees by a lattice path called the competition interface. So this is a notion introduced by Pablo Ferrari and Leandro Pimentel. So it's a lattice path phi n, and I'll denote its coordinates by phi nh and phi nv. This is an upright path that can be described precisely like this. So the end point on the path lies on the anti-diagonal at level m+1. And on that anti-diagonal, there's a unique point such that whose right neighbor is in the red subtree and whose up neighbor is in the blue subtree. And that marks the point where the competition interface is. In their original work, Ferrari and Pimentel proved that the competition interface has an asymptotic direction almost surely. And one can write down the distribution of this asymptotic direction. So this direction is random. So for example, the horizontal coordinate rescaled by n has this limiting CDF given by this function. Now there has been subsequent works, including these listed on the competition interface, but what I will focus on is this result by Ferrari and Pimentel. Now, our result is that one can quantify the speed of convergence here. So here's what we can do. So if you fix delta, then, and look at the difference between the CDF of the rescaled horizontal coordinate and the limiting CDF, then uniformly, when x is away from the boundaries, it's uniformly true that this is bounded by at most n to the 1 over 3, minus 1 over 3, up to logarithmic factors. So this proof relies on some comparison inequalities and the exit point bounds, the second exit point bound that I showed, applied with z parameter that's within n to the 2/3, a little more than n to the 2/3 away from the critical parameter. Now, we did not prove the lower bound, matching lower bound, but at least in my opinion, this reflects the correct decay behavior for this distance. Okay, and the next application I will mention is about is of a similar flavor, and I will now look at the limits of last passage increments in the bulk. So L denotes the last passage process. So I will look at the increments, keeping the terminal point y fixed, and looking at the increments with respect to the initial point x. So this B denotes the horizontal increment, and BV, I'll write BV for the vertical increments. So it's natural to think of these as edge variables and place them on the outgoing edges from the vertex x. Next, I will fix the direction vector u and choose this northeast vertex yn as n times u, essentially. Then I will let n go to infinity. So this will make this corner go to infinity in direction u. And then it's known that due to a result by Ferrari and Pimentel, it's known that these last passage increments, they converge. And we can call the limits Busemann limits. These are important in study of geodesics in this model. There's a lot one can say about the Busemann limits in this model. For example, it's known that they satisfy the Burke property. Note that the bulk LPP does not have this property, but in the limit, the Busemann limits, they satisfy this property. So meaning that if you take any downright path and look at the Busemann limits along those along that path, then those limits will be independent. Moreover, the marginal distributions are also known. So they are just exponentials, and with rates given by this critical parameter evaluated at direction u in which we take the limit. Now, in the result that I will mention shortly, for simplicity, I will just focus on this type of path, L-shaped downright path. So K and L will denote the horizontal and vertical, the lengths of these segments of this path. And as in the competition interface case, so I will be interested in quantifying the speed of convergence in distributional limits. So I'll now look at the joint CDF of the last passage increments along this downright path. I'll denote this with capital F. Okay. Now we know from the convergence result that this converges to some limiting CDF of the corresponding Busemann limits. And that's known explicitly. It's just this product of 1 minus exponentials. And our interest is to quantify the distributional convergence at the speed of distributional convergence. And one way to do this is to compare the CDF of the increments and the limiting CDF. Okay. Now, it turns out that if we also, so this is for technical reasons, so if you also allow K and L, which denoted the length of this L-shaped path, also to grow with the scaling parameter n, then it is easier for technical reasons to bound not the difference of the CDFs, but the difference of the modified CDFs that are obtained as follows. So I will just flip, for example, the inequalities here for the horizontal increments. And I do the same for the limiting CDF. So it's easier to work with this. This is due to the monotonicity structure of the last passage times. Of course, when K and L are fixed, this doesn't matter. Well, in any case, this contains the same information as the original CDFs. And when K and L are fixed, one can get the same bounds taking by doing finitely many operations. But when K and L also grow, then the bounds we can get for these modified CDFs is sharper than the ones we get for the original CDFs. And alternatively, one could have also flipped, of course, the inequalities for the vertical terms. Now, then, this is the result one can get. So if you look at the modified CDF of the last passage increments along that L-shaped path and compare it with the limiting CDF of the Busemann limits with parameter zeta, then the difference is essentially of order m plus n to the minus 1/3 up to logarithmic factors. So here, again, we restrict mn to be away from the boundary and should be sufficiently large, but also the sizes of the path can go up to m plus n to the 2/3. So here, again, it's likely that the bound is sharp up to logarithmic factors, but we did not prove the matching lower bound. There is also a related result by Marton Balázs over Busani and Timo Seppalainen that preceded this. And that's also of similar flavor. So they provide an upper bound of order n to the minus 1/3, 1/4, slightly worse, but in a stronger mode of convergence in the total variation distance of the LPP increments and the Busemann limits. And one other strength in their result is that they compare the increments and the limiting increments in an n to the 2/3 by n to the 2/3 rectangle. But here we only do this along a path of length n to the 2/3. Besides these, there have been some further applications of the exit point bounds that I showed. So for example, they have been used to obtain optimal coalescence estimates for geodesics in LPP. And they also are used as an input in a result by Busani and Ferrari, where they compare the geodesic tree in the bulk LPP and the corresponding increment-stationary LPP. Okay, so with this, I've concluded the discussion of the results, and I will just briefly say a few things about the technical aspects. Now, as I said before, the sharp right tail upper bounds for the exit points that we obtain here, they can be proved as in these references using this left tail bound as one input. So here we are looking at the left tail of the increment-stationary process with the critical parameter. And this deviation bound, so we are bounding the deviations of order s times m plus n to the 1/3. And what we need is that this goes down like e to the constant s to the 3/2. Now, this is not the true rate of decay here, so the correct rate is s³, but this is enough to establish s³ behavior. Now, our technical hurdle at the beginning of this project was that such left tail bounds have not been established via our method of choice, namely using just the increment-stationarity properties. However, we managed to find a substitute in the literature. There's an identity that goes back to work that was recorded in a preprint of Eric Rains in early 2000. It's an identity that relates the moment generating function of the LPP with boundary weights evaluated at certain exponents to an exact expression. Okay. Now, we do not establish this s to the 3½ decay for the left tail, but we use this identity to access the left tail partially, just enough so that we can obtain the exit point bounds. Now note that this identity, in this identity, if W is less than Z, the exponent is negative, so that grants some access to the left tail. Now, the original proofs of this identity, it utilizes integrable probability and relies on exact distributional formulas for the last passage times that I said we avoided here. Our contribution to this identity is that we observe this as a simple consequence of stationarity feature. Now, here, one may ask if this is limited to the exponential model, and the answer is no. In fact, versions of this identity were already known to Raines in his preprint for a variety of integrable models. And it's very likely that analogs of the identity can also be established in all the other models that I listed in one of the slides earlier. And the proof that this follows from increment stationarity can also very likely be adapted to all of these situations. So having an exponential weights is not a limiting factor. Okay. All right, so with this, I've come to the end of my slides. I'd like to thank you very much for your attention. And if you have any questions, I would be happy to try to answer.
Okay, so thank you very much. So I'd like to say that this talk closed with a cliffhanger, because now there was this wonderful identity, and I was actually ready to hear more, but
yes, so I can say a bit more. So I intended to keep the technicalities to a minimum, but is there a particular aspect of this that?
Yeah, for me, it's interesting to see how this identity can be proven. You know,
yes.
only from
right. Yes. So this identity actually. So the proof using increment stationarity is actually quite short. If you just change the measure on the horizontal axis in this expectation, so the horizontal axis, on the horizontal axis, the boundary weights have rates W. So if you change the measure so that the rates change from W to Z, then the expression you get in this expectation is just the expectation of the some exponential of the increment of last passage times on the north side, but now in the increment stationary model, because in the increment stationary model, W equals Z. So if you just express this as an expectation of the last increment stationary last passage times, then the integrand becomes an exponential of the increment. And those increments, their distributions are known. They are the same as the boundary weights. So from that, we pick up this factor, and this other factor, it just comes from the Radon-Nikodym derivative in the change of measure.
Okay. So, okay, thank you for this explanation.
So you use this formula for W less than Z to obtain tail bounds?
We do both, but you know, to obtain the exit points bounds, you want to, for example, let's consider the situation near the characteristic direction. So then the exit point would like to be near the origin. Okay. So when you try to bound the event that it's away from the origin, then you need to, in the argument, you need to actually compare some moment generating functions involving the last passage times evaluated both at positive values and negative values. This identity allows one to do something about the negative exponents. For the positive exponents, it also is useful, but is also useful. So in short, I mean, for both of these terms, this is basically underlying source of the estimates. But the more difficult part that was not previously accessible is the terms with negative exponents in this argument.
I see.
Yes, and I thought a bit about your question at the back of my head, but so it is. So it's not. It's a bit difficult to answer. I think I don't have an answer at the moment for this.
But you expect the S cube exponent to be tight, right?
Yes, yes, yes. In fact, for one of the bounds, I mentioned the matching lower bound due to other people. So, for example, for the increment for the characteristic direction, the matching lower bound has been obtained.
I see. Yes.
Yes.
Also, can you go back to the slide where you were saying comparing the CDFs?
Yes. For the Busemann functions, or
yeah, this one. So you were saying like it can be improved when K and L is also grows with N?
So I was saying that, so in this statement, I'm not comparing the CDFs, but modifications of the CDFs.
Yeah.
And if I just compare the CDFs, then we do not have this bound.
Okay.
We could have that bound if we just restrict K and L to be constant, not grow with them. But when K and L grow, are large, then we do not have the same bound for the original CDFs. So it is. So this comes from this is a technicality that comes from how the direction of monotonicity in the increments of the last passage times.
I see.
So if K and L were just fixed, using this bound, one can get the same bound for the original CDFs, just taking doing a finitely many operations. Yes, but when K and L are large, then those operations cost too much.
I see.
But here we were just. It may be possible to also get the sharper bound for the CDFs, but using a bit more than what we are using currently.